All right, so I am going to first go over this classwork exercise from your notes. You'll do, or hopefully at this point you have typed in all of the distances from Atlanta to all these cities, as well as the prices for these plane tickets. If you haven't, hopefully the sub can pause this and wait for you guys to type those in. So I am going to go through all the steps here to do all of this work with this data from Chapter 8. We just have finished up talking about Chapter 7, which was the intro to looking at scatterplots and the relationship between two quantitative variables. So we're going to go a step further this week, talking about a lot of different things. Most importantly, finding the least squares regression line, which is also known as the line of best fit, or a model that models the relationship, the linear relationship between these two quantitative variables. And then a lot of stuff comes from that, talking about correlation, the correlation, the R squared, which was when you square it, looking at how to interpret y-intercepts, slopes, words that you've heard before in other math classes, but in a stats concept, or a stats context, All right, so let's go ahead and begin by looking at finding the line of best fit here, or the least squares regression line for this data. So hopefully, again, you've typed in all of your pieces of information from the distance from Atlanta to these cities and the price that's associated with it. And so I'm going to show you how to create that. So first, we want to make sure that we think that there's a linear relationship going on. So really doing stuff from Chapter 7 or last week. So I'm going to hit Doc, Insert, and then I'm going to click Data and Statistics, number 7. So the first thing you have to decide is which variable is going to be your explanatory variable and which variable is going to be your response variable. Now I know for this example they've already created the scatter plot, so we already are going to, you can see we're going to use distance explains fare, or the price. And so that's really the way that I do this, is I say both. I say, okay, does distance explain how much the flight costs, or does the flight cost explains how far you're going to fly? So I try to say both sentences when I'm looking at a problem and see which one makes the most sense to me. So which one is explaining the other? All right, so we're going to use distance as the explanatory, or on the x-axis, and on the y-axis I'm going to put fare, which is the price. And you should see that it looks just like what you have on your paper. This is called a scatter plot. Now, last week in Chapter 7, I told you that we had our mantra for histograms, which was shape, center, and spread. That's not what's going on here, because this is not just looking at one of these variables. We're looking at the relationship between the two of them. So really what you want to be thinking is direction, form, and strength. So is it going up, is it going positive or a negative direction? Are we looking at something that's linear or not linear or curved? And then the last thing is looking at how strong it is. Are all of the dots here, all of these points, are they very close together, or is it a lot of scatter in terms of strong, weak, or moderate? So it's up to you again, just like with shape, center, and spread. It's your opinion. It looks like this is going in a positive direction. We have the shorter distances costing less money, which that probably makes sense in your head. So positive direction. It looks like there's a decent amount of scatter. And if you look at the worksheet, it says the correlation coefficient is 0.694, so just under 0.7. So I would not say this is strong. Maybe this is more of a moderate to maybe moderately strong relationship, linear relationship here. And then finally, I would say for the, form, I would say it looks linear, or linear enough that we feel comfortable doing all of these things. So again, if you look at this and it's not linear, if it's a clear curve, or if there's a significant bend in the relationship in the scatter plot, we would not do everything we're about to do. All right, that is going to be something we talk about in a few weeks, where we can actually re-express one of these variables on all of the data values, or maybe both, to find something that is somewhat linear, and so it makes all of procedure we do here appropriate. It's not appropriate if we see that there is not a linear relationship. So all of this has to do with linear relationship. All right, so because we're saying it's appropriate, then what I do is I create the line of best fit. So I'm going to insert a calculator page. So insert calculator. So a blank calculator page still in my same document. Menu. I'm going to go to stats, and I'm going to go to stat calculations. And you should see at this point, since we did in chapter 7 last week, we have moved from just one variable statistics, which is where we focused the first 6 chapters on that, and we're going to linear regression, which is actually number 3 and number 4. But in algebra, we use the form mx plus b, which is number 3. The reason we're not going to use that, and we're going to use number 4, which says a plus bx, is because some of you will take more advanced statistics classes in college, or maybe you become a statistician, where when you look at regression models, you're going to look at more than just one explanatory variable. So you'll have b sub 1, b sub 2. You'll have more of these things that you're looking at, which is why I want to get you in the habit of looking at just a plus bx, or number 4. So I'm going to click number 4. We said the explanatory was distance. The response, or your y value, is the price, or fare. And I want to point to your attention here. It says save regression equation to F1. We're going to use that later on. So if yours says F2, just make a note that you need to make sure that when you're typing stuff in, you use F2. But for mine, it says F1. Everything else you can leave the same. So I'm going to just tab down to OK. And then it's gone ahead and given me the regression equation. So if you look at your actual problems, if we go back to the actual problems here, 1 through 13, it looks like you can go to number 5, which is right here, and we can write down the equation of the linear model, which is going to be in context. So again, in context, you don't want to put y and x, you want to put what they represent. So this is where you're going to write for y, that was our price or fare, so fare, and because this is a predicted value, so when we make a model, this fare is going to be a predicted price, so I'm going to put what we call a hat, that means it's a predicted fare, equals, here is where I'm going to put my a value, which says 177.215, or 177.22, all right, it's positive. So you'll notice that the slope b is a positive number, and it looks like it's 0.078619. I'll just round to 0.079. All right, so plus 0.079, and that's going to be multiplied by, and this is where I want to put the actual explanatory variable. Don't just put x. So I'm going to put distance. So basically what I'm saying here is that we have looked at, if this is our model for this relationship, so this is our linear model for this relationship, even though it only gives you cities like Las Vegas, Miami, New Orleans, say you wanted to travel to a city that's not on here, doesn't look like Washington, D.C. is on here. So if you looked up the distance from Atlanta to Washington, D.C., and you found that distance, you could plug it in where it says distance into this model, and it would spit out a predicted price for that flight. Now again, it's predicted, and it's a model. And as you know, models are never true, but maybe it's useful. And actually, this is, in a simplified way, this is what airlines do to find a price that you're going to pay to fly from Houston to wherever you're going. All right, again, simplified way because we're only looking at the distance, and we're going to talk about later that there are lots of other things going on that factor into the price. Now, one thing that I want to make clear is you can do all this stuff, but it doesn't mean anything if it's not appropriate. So what I actually do is I insert another data and statistics page, because I want to make sure and check this, all right? Click the explanatory is exactly the same, which is the distance. But you'll notice that when I click to add my fare, other things have popped up. And this is after I have calculated that regression model or that linear model. So if you try to do this step before you do the model, it won't actually pop up. So there's 4 there that start with stat and then a period. The only one I want you to focus on is the one that says stat.resid or R-E-S-I-D. This is called the residuals plot. So we're going to click stat.resid, which basically, if I can try to explain this as best I can, once you have a model, it takes all of your x values, your distances, like you'll see for Baltimore, it says 568, and it plugs in 568 into that model we just wrote down. So it calculates a predicted price. Now that predicted price will probably not be the price it says, which is $2.19. That difference is called a residual. All right? So it calculates residuals for all of these cities and their prices. And this line that it's created for us, this linear model, is actually the line that minimizes those differences. So that's why another name for it, as I mentioned, is the least squares residual line. So it's trying to minimize those distances from the actual data points to the predicted values. All right? So the reason I want to check this, so there's stat.resid. The reason I check this is because if I see any type of pattern, like a fan shape, which we'll describe later on what that looks like, or a curve or a distinct curve, that would tell me that what I'm doing is not appropriate and I should stop. And as I said, we would re-express one of these variables. Okay, we would change the values. So again, you do want to check this step. You can see here in what I have that it doesn't look like there is a pattern. You're looking for a cloud, so just dots all over the place and no distinct pattern. That would tell you that this is appropriate to keep going. But again, if I all of a sudden see a pattern in the residuals plot, then I don't keep going. I'm going to re-express one or both of these variables, which is something we'll talk about in a few weeks. All right? So far so good. We have done number 5, which is writing the model, and so far we have no reason to believe that this isn't appropriate. All right, so let's go ahead and answer number 3 and 4, since we've already written down the equation. 3 says to find the slope and the y-intercept. Well, the slope, since this is in the form a plus bx, the slope is actually going to be the b value. All right, so our slope is 0.079, and our y-intercept is 177.22. Now, that's great, but really I care more about answering numbers 9 and 10. If you look to the right, you'll see numbers 9 and 10, which say, explain what these mean in context. Right? Just writing out the y-intercept is this number, the slope is this number, that doesn't really help us. You want to put it into the context of the problem. So in this problem, we would say that this slope of 0.079 means that every additional mile that you fly from Atlanta to a city, you can expect the price of your flight to increase by about 8 cents. So I'm going to repeat that because that is important, okay? Every additional mile, because the distance is measured in miles, so every time we add a mile in how far we fly from Atlanta to a city, we expect the price of this flight to go up by, and you'll see the slope is 8 cents. All right? So that is what we call explaining the slope in context. Now for the y-intercept, it's been a while since you probably were in algebra, but for the y-intercept, that assumes a distance of 0 miles. So literally you're traveling nowhere. So this is saying if you don't travel anywhere, it's still going to cost you $177.22. And that might sound kind of ridiculous, like why am I paying you $177.22 to go nowhere? But this is where all of those other costs for the flight come in, right? The company, whatever you're flying, Delta, United, Southwest, whatever company you're flying has to have paid for the plane or they're renting it out from Boeing. They have to pay for gas to get you there. Many times they pay for drinks, snacks, sometimes meals. Sometimes they're paying to haul your baggage, like Southwest, you don't pay for that, so it's included in the price. All of these things go into it, all right? So it's not just how far you're flying, it's also all those other things, all right? They also have to pay for the salaries, all right, of the people flying and the flight attendants that are on there. So again, all of these things factor in. It's not just distance. So that 177 includes all of those things that have nothing to do with how far you're flying. So the way that I think of it, and the next time you guys get on a plane, think of it like this. You're walking down the little terminal to get onto the plane, or the tarmac, whatever, and you get on the plane. That moment you step on the plane, you should just go cha-ching, because you have just paid them a lot of money just to get on the plane. All right? I always like to think that. All right. So we kind of answered 3, 4, and 9, and 10. And then I want to talk about R squared now. And then we'll get into 6, 7, and then those last couple, 11, 12, and 13. So let's talk about R squared. I'm going to go back to my calculator. And if I go to the tab that has my calculations, you'll see we've already used A and B. That was for the actual linear regression model. And then I see R, which is the correlation coefficient. That tells you how strong or how weak, so the strength of your linear, again, linear relationship. It's only about linear. And 0.694, we said that was, moderate, maybe to moderately strong. Nothing like a 0.9 would be pretty strong, or a negative 0.9 would be very strong, but in a negative direction. But R squared, if you look at R squared, it says 0.482. The way I want you to describe R squared is actually as a percentage. So I'm going to write down 48.2%, and that would be for, if you look up at your paper, number 1 or number 2. So 48.2%. And here's how I want you to describe R squared. So the way this works is when you write down for number 2, you're going to say 48.2%. So 48.2% of the variability in the price of a flight can be explained by how far you travel on the flight, so the distance. So I'll explain that again. So 48.2% of the change in the price of your flight is explained by the distance that you travel on that flight. So what we're saying is only about half of the fluctuation or the change in how much you pay to fly on a plane is determined by the distance you are flying. So let's think about that, right? Only half is determined by that. What other factors could come into play that determine the price of a flight? Well, sometimes I've heard this, and when I try to book flights, I try to do this. I've heard if you fly during the week, so like on a Wednesday, because that's not a very popular day to fly, that would be sometimes where they're getting people to fly, so they try to lower the prices. So during the week can usually be cheaper. Coming in on or flying in and out on weekends or Sunday night when it's popular, all right, they're going to bump up the price, so that'd be more expensive. All right, flying on holidays or to go somewhere for holidays like Thanksgiving, Christmas, Easter. They know spring breaks happen for schools. All those is we're going to bump up the price, all right, charge you more money because they know you'll pay for it. All right, you'll get into that with your econ class about supply and demand there. All right, so all of those things affect the price, all right, and have nothing to do with how far you're flying. Another one that I like to think of is the destination. If people like to fly there and they know people are going to fly there, they're going to bump up the price. All right, so think about where you're flying to. If you're flying to popular cities or big cities, a lot of times those are going to be more expensive as well. All right, so I feel like we maxed out almost all of this problem. I do want to show you some cool things about number 6, 7, and then 11, 12, and 13. So it says to estimate the fare for number 6 of a 200-mile flight. So check this out. If you go to your calculator, I'm in my calculator page, so make sure you're there. If you remember, it's been a while, but this was saved, this equation was saved into F1. So if I type F1 and then parentheses and type in 200, it will spit out how much money it should think they would charge you to fly on that plane. So $192.94. So if you do the same thing for number 7, so you do F1 of 2,000, it says you should expect, again, I don't know what you're going to pay. This is what the model predicts you're going to pay, $334.45. So all of this stuff is amazing in the calculator because you don't have to take, 200, you multiply it by 0.079, then add 1 is 77.22. It does it all for you, all right, if you use the calculator. Now, let's talk about residuals. So numbers 11, 12, and 13. So just as a reminder, all right, from your textbook and stuff you have been reading about, a residual is the difference between the observed minus the predicted value. Okay, so again, the observed minus the predicted. So as I told you about how the computer, the calculator, creates this line, all right, they are trying to minimize, all right, or keep as small as possible the residuals for every single one of your data values. Okay? So it says the fare to Los Angeles is 1,719 miles from Atlanta. So if you look at, it's not even on here, this is an additional one. It says the price to fly there is $212. So find the residual. So this would be the observed price. So $212 is the observed price. So I can type in the distance of 1,719 miles into my equation to find the predicted. I'm going to type in 1,719. So F1 of that distance, 1,719. So the model predicts that it should cost $312.36. So that's what we call the predicted value. So 312, all right, I forgot. We'll just round it 312 since they gave 212, but 312.36, okay? So the observed is 212. The predicted, this is the predicted here. So to find the residual, it would be negative $100. Okay? So negative $100. Now let's talk about what that means, and this is really what we're going to say is going to answer number 13, because it says a negative residual means. Well, what did we pay to fly from Atlanta to Los Angeles? We paid $212. What did the model say we should expect to pay? It says we should expect to pay $312. So if you get a negative residual in this context, that means amazing things for the consumer. The consumer is getting a deal. All right, I am paying less money than what the model expects me to pay. All right, so that's good. So in this context, again, because it could change in other problems, I want a negative residual. That means I'm paying less money than the model thinks I should pay. Now, vice versa, if you look at 12, a positive residual, so that would mean that your observed value, what you're actually paying, is more than the model predicts. That would mean the consumer is paying more than what the model is expecting. So that would not be what we want. We do not want a positive residual in this problem. That means we're overpaying than what the model expects us to. All right? So a lot of good stuff to talk about there. And I understand that I'm going really fast because I'm not here, but I will have this on YouTube and you can listen to it. We're going to do this process a ton. And even if you're still confused, we will do this again in Chapter 9 and Chapter 10. So this whole process will be repeated of how to look at the relationship between these two quantitative variables.